right, so chapter 2 here for AP Biology is going to go over basic chemistry. What we're talking about here is all the molecular properties that are going to influence life in general. So let's just jump into it. Remember, this is section 2.1, which means this is what we'd go over in the first day. So let's talk about a couple different terms here. Matter, this is anything that has mass and takes up space. They can usually be in a solid, liquid, or gas. You learn in chemistry that it can be also a plasma, but we try to focus on just those solid liquids and gases in here. We go over in chemistry very surface level or very just simple chemistry understandings and applications. We're not diving into these deep, complex topics within chemistry. We're staying surface level, very easy stuff. Elements, these are substances that cannot be broken down further into simpler substances without changing their properties. So basically what this means is our elements are going to be a substance that is just going to be very common among all elements, but there is some variability there, but you can't really break it down without changing its properties. Elements are made up of tiny particles called atoms. You should know about the atomic theory from chemistry, but just basically elements are made up of atoms. The most common elements in life are carbon, hydrogen, nitrogen, phosphorus, oxygen, and sulfur, and they make up about 95% of your total mass. CHOMPS, CHN or ONPS, this is just a way of remembering it. You can see we were made up a lot of oxygen, carbon second, hydrogen, nitrogen, and then the others. But you should definitely know those top four: oxygen, carbon, hydrogen, and nitrogen. All right, so talking a little bit deeper within the atom and the atomic theory, we have these things called subatomic particles. That means they are very small and they're smaller than an atom. And we have protons, electrons, and neutrons. Protons are positively charged, electrons are negatively charged, and neutrons are neutrally charged, or they don't have a charge. Just a reminder, we're not going deep down into this understanding of the atom, why is a proton positive? Why is an electron negative? I don't need you to know that. I just need you to know that they are negatively and positively charged. Remember that this is not a great representation. We have to give this representation because it's like a two-dimensional screen, but they don't float around. These electrons don't float around the nucleus like a solar system, but this is just how we have to represent it in this PowerPoint. Remember that protons and neutrons are in the nucleus, while electrons are in the electron shells. Or the orbitals, however you want to name it. Protons and neutrons both have an atomic mass unit, AMU, of 1, while electrons have an AMU of 0. So they don't, like electrons, they do have a mass, but it's so small that we really don't, we don't talk about, I want to say talk about, in biology, we really don't focus on it because it's just so small. All right, atomic number, the number of protons in the nucleus. This determines many of the unique properties of that element. That atomic number is usually found on an element, like on the periodic table above the element symbol. The mass number, the number of protons and neutrons in the nucleus. The atomic mass, the average of the mass numbers of all the isotopes. So that's why this one's just a little bit under 16. Is because if you average out the different isotopes, you're just going to get a higher under 16. Chemical symbol, this is just a 1 or 2 letters that represent that element. If it's they try to make these element symbols like the word is for oxygen, but if they can't because there are several elements that have the same starting letter, they may use its Latin name or just a Latin symbol or another letter or letters to represent that element. You can see here's a very basic periodic table, which we're going to talk a little bit about. But you can see atomic numbers on top, the atomic mass is on the bottom, and then you have your element symbol here in the middle. Oh, let's go back. Let's talk about one more thing. Periods go up and down the periodic table, and groups go across. People say atoms aren't important, but they matter. You'll see that I have a lot of memes in my PowerPoints. I try not to use the memes or show the memes in these videos, but I'm just going with my videos right now, or my PowerPoints right now. So isotopes, these are atoms of the same element with different neutrons. You can see that we have carbon 12, 13, and 14 up here. Carbon 12, you can see we have 6 protons, 6 neutrons. Carbon 13 has 6 protons and 7 neutrons. And carbon 14 has 6 protons and 8 neutrons. You can see the number of protons stays the same, but the number of neutrons differ. And you can see we're adding one for each neutron that we're adding here. So, let's say, go back to your carbon 12 has 6 and 6, which equals 12. Carbon 13, 6 and 7, which equals 13. And then carbon 14 has 6 and 8, which equals carbon 14. These percentages here are the relative abundance of that isotope on Earth. So you can see most of the carbon that we have is in this carbon 12 4. One thing I want to add in here with the periodic table, there are 118 elements on the periodic table, and they're organized by the atomic number and their properties. So, we start here with one with helium, one with hydrogen, two with helium, going too quick, three with lithium, four with beryllium, and I'm not going to go through all of them, but you can see as we go up the periodic table, or I should say down the periodic table, we're increasing in the atomic number. And remember, the atomic number represents the number of protons in the nucleus. Now, we have two specific ways that we organize it, by periods and by groups. We have many more than just that, but we like just to kind of start out with periods and groups. Periods are the horizontal lines across the horizontal elements. These don't share chemical properties, and actually they vary greatly between each element. But groups somewhat will tend to have similar properties because they have the same number of valence electrons, which we'll get to. All right, difference between molecular formulas and molecular structures. The formula is just what is made up in that molecular compound. You can see butane here. The molecular formula is C4H10. Also, isobutene has C4H10. The molecular structure, though, of these two is different. You can see how we're structurally different compared with butane and isobutane. Even though we're made up of the same elements, the actual structure here is different. All right, molecules and compounds. A molecule is any combination of elements connected by bonds. Compound, these are molecules that include more than one element. It sounds like the same thing, but let's talk about how they're different. All compounds are molecules, but not all molecules are compounds. So over here, I have a great representation of what I'm talking about. So each sphere here is an atom. You can see here we have this molecule. It's also a compound because it's made up of more than one element. Molecule and a compound, there are more than one element and they're connected together. This is a molecule, but it's not a compound because it's only one type of element. So you can see here compound because, again, it has more than one element and it's connected together by chemical bonds. And when you have more than one compound, it's known as a mixture. We don't get really deep into mixtures, but I do want you to understand the difference between a molecule and a compound. Compound basically has just different elements. All right, isomers. And if you see here, we jumped into 2.2 molecules and compounds. I didn't really stop and talk about that, but we did jump into a second section here. Isomers. These are organic molecules that have identical formulas, but different arrangements of atoms. You can see we have the molecular formula here, C2H6O, C2H6O. They have different structures, though. And I know it might not seem like it's very important, but these are very important. Even changing one element's location in a compound can drastically change the properties of that compound or molecule. Let's talk about valence electrons. These are the electrons that are found in the orbitals the furthest away from the nucleus of an atom. You can see here this image showing us the valence electrons on the outermost orbital. One easy way to determine the number of a valence of electrons for a particular atom, for a particular element, is by looking at a periodic table. So here's our periodic table. We have 1, 2, 3, 4, 5, 6, 7, and 8. But be careful, helium only has 2. These ones in the middle and these ones here at the end, we don't usually, if I ever would give you like one of these to figure out, which I won't, I would tell you like, hey, this has 4, 3, 8, whatever, because they're kind of random in here. But basically just remember that these periods have like 1 valence electron, 2, 3, 4, 5, 6, 7, and 8. Atoms typically want to have 8 valence electrons, not always. There's so much just variance within chemistry. Like these first two, helium's fine with 2. It's happy with 2 because its orbital, its innermost orbital is filled. We won't get into that kind of detail with chemistry or with the chemistry in biology, but I want you to kind of remember this aspect, this concept from your chemistry classes. Take a look a little bit into the like the number, like we talked about with atoms want 8 valence electrons. Atoms can gain or lose valence electrons to complete this rule. The electrons can be shared or given to another atom. So you can see here we have like hydrogen with 1, carbon with 4. We can add these hydrogens to carbon, like down here in ethylene, or we can add these hydrogens to like an oxygen for water. So these dots here represent those valence electrons. And these lines are going to represent the bonds that those valence electrons form with different atoms. So you can see here, this is water. We have 2 valence electrons. Here's that bond here between oxygen and hydrogen. Like we said with these dots, what we're building here is something called a Lewis dot structure. And this consists of the element symbol and the number of valence electrons. And there's a specific way that you make these valence electrons. I should be, I hope that when we're going over this, you're like, oh yeah, I remember all this from chemistry. But we have 1, then we have 2, 1, 2, 3, 1, 2, 3, 4. Notice how we're kind of separating them up until 5, then we start pairing them. These are paired electrons. These are kind of just like single electrons. They're not bonded with anything yet, or they're not like kind of paired with another one. But this is the way we order the valence electrons. Now, like I said before, the lines between these valence electrons, or I'm sorry, these lines between the atoms represent bonds between the atoms. So you can see there are 2 of these electrons that are being either shared or given between these atoms. And then we have a pair of electrons here below nitrogen. So these lines are just representing those electrons that are interacting in some way. We're going to talk about next how they interact. Let's talk about the different types of chemical bonds that we're going to see in chemistry. So we have ionic bonds and we have covalent bonds. We're going to start talking about ionic bonds first. This is a bond where atoms are going to be held together by an attraction force between a negative and positive ion. Remember, we have these valence electrons and we have these Lewis dot structures. Sodium has 1 valence electron. Chlorine has 7. It wants 8. So what's going to happen is sodium is going to give chlorine an electron, which means it's going to have 1 less electron, which means it's going to have a positive charge because there's going to be more protons than electrons. In chlorine, they have 7, so they're going to get that 8th electron. It's going to become just a little bit negative because it has an extra electron, which is negative, and it becomes a negative ion. And then there's going to be an attraction force between that positive and negative atom. Now, this is a very weak bond, but this is when electrons transfer or give their electrons to another atom. Let's talk about covalent bonds now. This occurs when the atoms are going to share electrons. You can see carbon here has 4 valence electrons, 1, 2, 3, and 4. It wants to have 8, so it's going to share these 2 electrons from this oxygen atom and these 2 electrons from this oxygen atom. They're actually going to the orbitals aren't going to share the electrons. It looks like they do here. They kind of do. It's tough. All you got to know is in these type of bonds, they share, and this is a much stronger bond. You have a single bond, you can have a double bond or a triple bond. Remember that between these two atoms, that bond, there are 2 electrons for a single bond. So like a triple bond is going to share 6 electrons. All right, polarity. This is something that's very tough to understand, and I don't think I had a great understanding until even after college teaching this stuff about polarity and electronegativity. We're going to start out understanding with polarity. There's an unequal sharing of those electrons when you have a covalent bond. What you can have is you can have electron-rich or electron-poor regions, which creates a negative or a positive charge. This is based on where those electrons are going to more hang out with. Here's a periodic table that shows you the electronegativity of the periodic table. Fluorine is the most electronegative element on the periodic table. We're going to dive more into the polarity in class, so just understand that polarity is the unequal sharing of electrons. All right, let me go back. Non-polar covalent bond. This is when a covalent bond has atoms that share the electrons equally. And so you can see oxygen is an example of a non-polar covalent bond. CH4, methane, this is an example of a non-polar covalent bond. A polar covalent bond is when the electrons are not shared equally. And this is when you get that electronegativity where we have the positive ends and the negative ends here. Most molecules will be polar. Not saying all molecules will be, most, but we're going to dive again deeper into this in class and do a little bit of review with the polar versus non-polar properties. Talking about polarity, polarity of water, water is very polar. It's because there's an unequal sharing of those electrons, like we just talked about. But what that creates are these things called hydrogen bonds, which are just a weak attractions between the water molecules. Let me go back here. And these weak attractions are just because of the negative and positive electronegativity of the water molecule. You can see oxygen is very electronegative. Hydrogen is very electropositive in this water. So what that creates, and I'll show you here, are these hydrogen bonds, which are very weak. They're the weakest of the bonds that we're going to talk about, but they form between the electronegative and positive ends of different water molecules. Now, why is that important? Well, that makes water a really good dissolver of molecules. Let me go back. Um, like dissolves like in chemistry, and what we see is polar molecules being able to be dissolved by other polar molecules, and water is very polar, so it dissolves a lot of different things. That's why we use it as it dissolves like as with washing our hands, and just as anything with cleaning, because it dissolves and really breaks down a lot of molecules because of its polarity. Now, we also have other attraction forces within water. Cohesion is when water molecules are attracted to each other. Adhesion is when they're attracted to things that are not water molecules. So this is just the difference between those two terms. And what it creates is a surface tension that's very high because of those attraction molecules, or I'm sorry, the attraction between the water molecules. Now, these water molecules, since they're so small and there's so much attraction between the water molecules, that's what really creates that high surface tension. Yeah, you should remember these things from chemistry. I'm kind of going through this quickly, but you should remember a lot of these. Because there's that attraction force and how the water molecules freeze, the density of water when it's a solid, so ice, is less dense than when it's a liquid. Now, we all know that ice floats, right? That's something we can see. But why does ice float? Because again, look at the density here. When water freezes, it forms these crystalline structures and it becomes less dense. Water as a liquid is more dense, and you're like, okay, well, you're telling me ice floats. That's common sense. But understand, not a lot of things in its solid form float compared to its liquid form. A lot of things will sink. In water's case, it floats, which makes it very unique and a property that really we need as a Earth to survive. If water would sink, our oceans and our lakes and our rivers would freeze over, and life couldn't survive. It actually insulates the life below, which is good for us because we need the oceans to not freeze over. If the oceans froze over, we wouldn't be here. So this is just a unique property of water that we need for life. Let's talk about the acidity or the pH scale of a solution. So this is a range of 0 to 14. Below 7 is acidic, above 7 is basic, 7 is neutral. But basically, this measures how much or how acidic or basic a solution is. 7 is neutral. That's pure water, and we'll talk about why it's neutral here in a little bit. But what I wanted to focus on here is the logarithmic scale of the pH scale. Each scale or each step is 10 times weaker or stronger than the last step. So pH of 7. pH of 6 is 10 times more acidic than 7. 5 is 10 times more acidic than 6. 5 is 100 times more acidic than 7 because you have to multiply 10 times 10. So like if we're going from 7 to 4, it's times 10 times 10 times 10, which is 1,000 times more acidic. So that's what it means by being a logarithmic scale for the pH scale. Now, let's talk about the ions and why we call each of these or what we call a hydrogen hydroxyl ion. So when water ionizes, it kind of breaks down into something called a hydrogen and hydroxyl ion. Here we have a hydrogen, here we have a hydroxyl ion. So pHs, let me go back, that are acidic have an excess or a large amount of hydrogen ions. Solutions that are basic have an excess of hydroxyl ions, and neutral ions have even amounts. You can see here on our pH scale ones that are more acidic, ones that are more basic. I'm just going to kind of breeze through that here. Last term that I want you to know is a buffer. We'll talk about more about buffers in class, but buffers are a chemical compound that keeps pHs within a certain limit or normal limit. For example, your blood has a normal average pH of 7.4. You have a carbonic acid within your blood that keeps your blood at a quote unquote average acidity. It doesn't matter what you eat, what you drink. Your body will retain that quote unquote normal limit for the pH. Your body has evolved ways to keep your pHs at certain levels. You don't need to be, drinking. There's a lot of misinformation out there about keeping your body at, oh, you need to do this or eat this and not eat that. Your body has a great way of doing that on its own. So these are called buffers, but we'll talk about them a little bit more in class.